So in this lesson, we're going to focus on galvanic or voltaic cell. A galvanic or voltaic cell is simply a spontaneous oxidation reaction, or what we now know as the transfer of electrons. It uses a thermodynamically favorable reaction to generate or harness an electric current. A voltaic cell is simply a battery. A battery is a device that uses a chemical energy to convert it into electrical energy. So let's say you have a battery here and you connect it with a wire and a light bulb. So there is a chemical reaction inside the battery and it will convert it into electrical energy. So let's say this is the positive terminal of the battery and this is the negative terminal of the battery. So the electrons will likely to flow from the negative terminal to the bulb towards the positive terminal of the battery. So as you have the moving of electrons, you have the current flow, and the flow of the charge can be used to light up the bulb or to do an outward. So that is basically what an electricity is, the moving of electrons or the flow of electrons. So every time you power up your cell phone, your laptop, or even your computer, and the battery is using a chemical energy to convert it into electrical energy. So that's how work is done. So a typical galvanic cell is composed of two half cells. So let's say we have two bakers here, and these bakers is both contains an electrode. An electrode is simply a metal. Metal conducts electricity. So let's say we have zinc metal on the left side and copper metal on the right side. So with these two metals, they have to be in contact with the solution. So let's say we have on the left side we have 1 molality of zinc sulfate. Also, we're going to connect these two electrodes in a wire and a voltmeter. And also we're going to need a salt bridge to prevent a build-up of charges between these two solutions. So let's see how does this work. So copper has a strong tendency to accept electrons, whereas zinc metal is like to give away its electrons. So the zinc metal is going to lose its electrons, so it's going to turn up into a zinc 2+ ions. So you need to remember that whenever metal loses electrons, it's undergoing the oxidation. And we need to remember that oxidation always occurs at the anode. So the other electrode has to be the cathode, and reduction always occurs at the cathode. So the copper 2+ ions here will acquire electrons, so it's going to turn up into copper metal. So to better remember this, just keep in mind the word anox and red cut, whereas oxidation always occurs at the anode and reduction always occurs at the cathode. So an oxidation is basically the loss of electrons, whereas a reduction is the gain of electrons. To determine this, let's just look at the oxidation number of the element. So we have in the zinc metal, it went from 0 to 2+. So there is an increase of an oxidation number. So every time there is an increase of oxidation number, it's undergoing oxidation. Whereas in the case of copper, we have it undergoes from 2+ to 0. So the oxidation number decreases, so it's undergoing reduction. So these two reactions, also known as half reactions. And you can easily tell if a half reaction is an oxidation reaction or reduction reaction by just simply looking at the electrons. So if the electrons are on the right side, you are having a oxidation reaction, whereas if the electrons are on the left side, you have an reduction reaction. So that's how you tell. So we now know that zinc is giving away its electrons. So electrons will flow from the anode towards the cathode. So because electrons is leaving the anode has to be negatively charged, because electrons always leave from the negative terminal of the battery and will flow towards the positive terminal of the battery. So the cathode has to be positively charged because the electrons are flowing into it. So let's see what's happening between the zinc electrode and the solution. So as we say earlier that the zinc metal is losing its electrons, so it becomes zinc 2+. So let's say we have a zinc atom here and it's like to give away its two electrons. So the zinc atom here will leave this electrode and it will get dissolved into the solution. So on the other side, we already have the copper 2+ in the solution. So the copper 2+ will be attracted to the incoming electrons that flowing from the anode to the cathode. So the copper 2 plus will acquire electrons and it becomes a copper metal. So over time, you notice that the cathode is getting bigger because the copper 2 plus is depositing themselves into the surface of the cathode, so it's getting bigger, whereas in the zinc electrode it's getting smaller. In the galvanic cell, the anode loses mass, whereas in the cathode it gains mass. And make sure you understand that. So there is another element that we need to talk about. It's the salt bridge. So what's the purpose of this? Why do we need this? So the purpose of salt bridge is to keep these solutions neutral. Let's say, for example, we have a sodium nitrate in the salt bridge. So as the electrons flow from the anode to the cathode, this side here, this half cell becomes a negatively charged, while on the left side it becomes a positively charged, because as the zinc atom leave the electrode, we have an accumulation of zinc 2 plus ion in the solution. So the nitrate, which is a negatively charged particle, is gonna go down to the left side of the half cell in order to balance the charges. So on the right side, as the copper 2 plus is deposited into this electrode, we have an accumulation of sulfate, which is a negative charged particle. So this becomes a negatively charged half cell. So the sodium, which is a positively charged cation, will go down here in order to balance the negative charge accumulation of particles here. So that's the purpose of salt bridge. It balances the charges between these two solutions. And in galvanic cell, if you remove the salt bridge, the moving of electrons will stop in the wire. So that's the purpose of this salt bridge here. It balances the charges between these two half cells, and it is necessary in galvanic cell because if you remove salt bridge, electrons will stop moving in the wire. So it brings us to the last component of our galvanic cell. We have the voltmeter. So in this particular galvanic cell, we have 1 molar of zinc sulfate and 1 molar of copper sulfate. At 25 degrees Celsius, the initial voltage would be 1.10 volts. That's what will show up in the voltmeter. We've talked about how galvanic cell works, so let's discuss the cell potential and how to calculate the overall net reaction. So we saw earlier that we have the zinc metal that turns into zinc 2 plus ions because it's like to give away its electrons. And for this half reaction, we have the cell potential 0.76 volts, and it's the anode. This is the anode, so it occurs in the oxidation. And but we have the cathode. We have the copper 2 plus ions, and which is likely to acquire electrons, so it becomes copper metal. And the cell potential for this half reaction, we have the 0.34 volts, and this is the cathode, so it occurs in the reduction. So to calculate the overall net reaction, we just simply have to add these two half reactions. So this gets to cancel, and we have on the left side we have zinc, sorry, 24 plus copper 2 plus iron, and aqueous solution. So the right side we have copper, which is in 24 plus zinc 2 plus iron, that goes in aqueous solution. So to calculate, so this is the overall net reaction. So to calculate the cell potential for this overall net reaction, we just have to add these values. So 0.76 volts plus 0.34 volts is equals to 1.10 volts. So this is the overall cell potential for this overall net reaction. And cell potential looks like this, which is equal to 1.10 volts. So that's how to calculate the cell potential and the overall net reaction for these two half reactions. In galvanic cell, the cell potential has to be positive, and whenever we have a positive cell potential, we have a spontaneous reaction. On the other hand, if we have a negative cell potential, we have non-spontaneous. So since this particular galvanic cell, we have a positive cell potential, so it occurs in a spontaneous reaction. Let's try another sample problem. For example, we have we have this overall net reaction, and we're going to identify the half cell reaction and the cell potential. So this is the diagram of the galvanic cell, just like what we did earlier. We have two beakers here and two electrodes, a metal electrode, and we have the anode and we have the cathode, and we connect it with the wire and a voltmeter, and we have a solution of 1 molar of zinc sulfate on the left side and 1 molar of iron sulfate on the right side. So we know that the electrons always flow from the anode to cathode, and we know that anode always occurs at the oxidation and cathode always occurs at the reduction. So the salt bridge will balance the charges, and the nickel 2 plus ion here will go on the right side to balance the negatively charged particle on this side. So the sulfate from this side will go here to balance the positively charged in this solution. So that's the function of salt bridge, and we have the two half reactions. So that's this. Again, to calculate the cell potential for both of these half reactions, you just have to add them, and this gets to be cancelled. So we have this overall net reaction, which was already given earlier. So to calculate the cell potential of this overall net reaction, we just have to add these two values here, and positive 0.76 volts plus negative 0.44 volts is equals to a positive 0.32 volts. And so this is the cell potential for this overall net reaction. And we know that in galvanic cell it has the cell potential has to be positive, so whenever we have a positive cell potential, we have a spontaneous reaction. So this is a spontaneous reaction because we have a positive cell potential. Review some important factors. In galvanic or Voltaic cells, it uses a thermodynamically favored redox reaction. It occurs in a spontaneous redox reaction, and this reaction generates an electric current through the flow of electrons from the electrodes. And the electrode where oxidation takes place is called the anode, and the electrode where reduction takes place is called the cathode. We just have to remember the term anodes in the right cut. And we also have the salt bridge. This balances the charges between the two compartments, and eventually the reaction will reach equilibrium, and at equilibrium the voltage is equals to 0. That means that there is no more current flowing in the wire, and the galvanic cells or the voltaic cells will stop working at that time.